MATLAB, Simulink, and StatFlow for function development in compliance with ISO 26262. This is the phase model for software development based on ISO 26262. It starts with the technical safety concept, goes over to the specification of software safety requirements, software architectural design, and unit design and implementation. After that, the software unit verification shall be done based on requirements. The software integration shall be done and verified. The software will be tested on the embedded system. And at the end, the system will be integrated and validated. With the model-based design, we'll cover a big part of it. For the product development at the software level, the central object is the model. So we need to understand the verification methods which are requested by the ISO 26262 for compliance. We need to define the pass-fail criteria and produce the verification reports for evidence. It looks simple, but there are a lot of model modifications which will be needed, and the usability shall be provided to do all of the iterations. Sometimes there are exceptions, and we will talk about the deviation procedures. Because of multiple iterations, it is important that the developer remains in the flow and does not waste time. All of this is provided by model-based design. Let's dive into it. The software development tool chain shall be qualified to make sure that no defects in the tools will impact the production software. We'll discuss the qualification kits, validation reports, and the different processes of tool qualification. In the context of ISO 26262, the tool qualification is the responsibility of the developer and not of the tool vendor. But the tool qualification kits, provided by the tool vendors, help integrating the tools into a customer-specific tool chain. We will talk about the formal inspections on the model level. Most people don't like them. They think it's a waste of time. But we will see that model views, which are the exports of models provided in the HTML format, allow offline inspections and collaboration, support deviation handling and documentation. Such views accelerate the formal inspections and the development processes altogether because they require no licenses and can be viewed in regular web browsers. The specification of requirements is the basis for compliant development. The models can be defined based on the requirements, and we can trace the requirements down into the model and back to the requirements. So the executable specifications help understanding the requirements at all system levels. The developers receive a new in-depth perspective on the system development if they define the requirements in the semi-formal notation and model those. The executable specifications help define clear system interfaces at all system levels. The system interfaces can be traced into the model. The full definition of the interfaces allows code generation. The model-based design gives you the ability to verify compliance of interfaces. The semi-formal notation provides graphical perspectives and enables modular approach for the unit-based development. The reviews are simple. You can print it out. At the beginning, you do not need to provide all of the information. But the semi-formal notation will help restricting and documenting the system context so that all project participants will understand the requirements much better. The model-based software architecture simplifies the impact analysis. You can visually trace signals to destination or to source. It's impossible in static tools like Visio or PowerPoint. So semi-formal notations and Simulink improve maintainability and impact analysis at all system levels. You can model timing behavior on the architectural level. Single-tasking scheduling with multiple rates and multitasking scheduling are supported. The semi-formal notations enable explicit mapping of complex rate control to the call tree. The software unit design and implementation is the next phase in which the software units will be derived from the architecture. You can model the software units as specified and define the requirements IDs. The semi-formal notation allows description of the functional behavior and the internal design to the level of detail necessary for their implementation. It means that the production code generation is then fully supported. Software unit verification shall begin with the static model analysis. It means that you can use specialized model checkers to improve the readability and the functionality of your models. Static model analysis is the most effective way to avoid design errors. Test-driven development begins with the definition of requirements in natural language and models. Such models can be executed, so we call them executable specifications. To verify the models, we need the requirements-based tests. Model-based design supports semi-formal verification, control flow analysis, data flow analysis, static analysis, and interface tests. Software verification requires test cases for each requirement. You can describe your test goals, the requirement IDs, the time and input vectors, the reference values, parameters, ignore data, and tolerances. Test specifications can be enhanced with simulation results for better usability. Verification reveals problems in the models. So sometimes you need to debug your models. With the integrated step-by-step debugger, it is possible. You can view block outputs for each time step, follow relevant signals on scopes and viewers, jump to a relevant time step, and highlight the signal path. Step-by-step debugger simplifies the impact analysis and problem localization. The analysis of structure and boundaries is possible with tools like Simulink coverage. You can measure decision coverage, which is the same as branch coverage. You can measure the modified condition decision coverage, which is a very sophisticated over-engineering metric. And you can measure the coverage of interface design ranges. So coverage metrics for model structure and interface boundaries define the test completion criteria. You can localize structural model problems in a debug mode. Here you see how the model turns from red to green over the test sequence. At the end, the complete structure is tested. The requirements traceability matrix provides the answers for the following questions. Where are the requirements implemented? Where are the requirements verified? And what are the verification results? The requirements matrix simplifies inspections and assessments. The software unit verification report might be needed for offline analysis. Dynamic signal plots are important for the understanding of model behavior. You can integrate interactive data plots into your test cases and highlight thresholds and tolerances to enable offline signal debugging in the regular HTML files. The verification reporting provides the metrics for test objects, test harness and test environment, requirements traceability matrix, full interface definition, simple version control, use in the web browser, and test data with plots. Verification reports provide the evidence of verification activities for assessment. Software verification on the model level can be done in different modes. The simplest mode is the open loop simulation. The more complex reactive mode would be using the bypass or feed-through signals from outside the test harness. It means from Simulink. And this feature allows the closed-loop simulations with plant models, which will generate test signals. And you can still use your test assessments. Reactive testing allows constructing all possible system scenarios and simulate the behavior in virtual prototype. The software verification can be done in model in the loop, which means that you just execute your model. Software in the loop, which means that you generate C code and embed it into the model again. And now you execute the C code on your host platform like Windows. You can also use your host debugger like Microsoft Visual Studio. And if you use your target compiler, you can compile the code and run it in the processor in the loop simulation, which means that your sources run on the target hardware. You can use the Trace32 simulator from Lauterbach or even the complete hardware debugger. C sources can be used and tested with existing test cases in different environments by using native compilers, profilers, and debuggers. You also can test your software in the hardware in the loop environment, which means that the complete software is tested in the target environment and in real time by using the partially or fully integrated electrical systems of the vehicle. The other names for such setup would be the lab car, the mule vehicle, and the rest of the bus simulation. The product development at the software level becomes very comfortable with model-based design. All verification methods are provided. The pass-fail criteria are defined. The verification reports are generated. The model modifications are simple. The deviation procedures are regulated. And the iterations are well supported with great usability. The software development will become a pleasure.